something happened. Anyway, great.
All right, go ahead.
Okay, well, it's about plastics, sustainability, biodegradability, and microplastics. So show you this first picture. You probably have seen it before. It's from Greenpeace. And because of pictures like that, plastics have been getting very, very bad press. Now, I have divided my talk in the following sort of subsections. First, I'm going to analyze a problem. Then I'm going to talk a little bit about statistics, pollution, production, recycling, biodegradable plastics, pollution from tires, fabrics, and microplastics at the end. First, a bit of terminology. Polymers versus plastics. Polymers can be natural or synthetic. They're really macromolecular materials, whereas plastics are synthetic polymers, which are compounded with a lot, I say a lot of fillers, reinforcements, additives. I can start talking about antistatic agents, UV protectors, colorants, name it. And of course, those additives, they participate in the problems that we have with plastics. Now, plastics can be subdivided in two categories. Thermoplastics, which can be remelted, they are solid, they normally delivered to the plastics processing plant in the form of pellets or powder. They get melted. They are shaped to the everyday products that we know. And they can be remelted many, many, many times. Okay? Thermosets, on the other hand, they harden with heat and cannot be melted. So they are not terribly recyclable. They are not recyclable really at all. However, the vast majority of plastics are thermoplastics. Now, my problem. I'll take this, try to analyze the problem, and perhaps address the issues regarding pollution, microplastics relating to water and soft drink bottles. The production is huge. 585 billion bottles are projected. More than 500 billion bottles are projected for 2021. All right? How does this thing start? The start is in the late 70s or early 80s, when the Coca-Cola bottles were exploding, 1.5 liter bottles. You do not have to do very much with it. All you have to do is tip it. And this is a professor from the University of Toronto. And he's got a protective, PMMA acrylic glass over there window, and he's tipping the bottle. The bottle exploded just by tipping it. And in fact, the shards went into the wood that is right here. So a terrible situation. In numerous jurisdictions, glass bottles were banned. And that really led to the, I would say, explosive growth of the plastic bottles, no pun intended. Let's take a look at the bottle and the twist-off cap. There are problems with this. Okay, the typical bottle, pretty much all of them are made of PET. Years ago, I remember in Greece, I had seen PVC, which is not a good material, but that was 20 years ago. Now, the bottles are made of PET, which is a very good material. The caps are normally made out of HDP, high density polyethylene, which is also a great material. We can make pipes of it, you know. The problem that we have is that in recent years, I have seen quite a percentage of caps which are polypropylene. HDP and PP, they just not compatible. They don't like each other. Polymers don't really like each other. And they have to be somehow separated. The separation of PET and HDP bottles, which are predominant, is very easy. PET sinks in water. HDP floats in water. But also polypropylene floats in water. So this has been bad news. Polypropylene in twist-off caps has really been bad news for recyclers. I know at least one company, they went out of business because they could not provide the good HDPE that they were providing in the past. It was mixed with polypropylene with inferior properties and whatever else. So they really went bankrupt because of simply that. Now, let's take a look at what happens with the bottles themselves. Some countries do an outstanding job in recycling, like Norway. Sweden also, Japan, and even India, they are doing very, very well. United States, not so well. Roughly about 30% of bottles are recycled. The rest of them end up in landfills or wherever, I don't know. But there are things here can be improved. More recycling of bottles. Now the bad news, very bad news. This is, this particular slide is from Forbes magazine. They produced this picture, an artist produced this picture, and it gives you some kind of a perspective. The work was done at the State University of New York at Fredonia by professor of geological, I think, engineering, Professor Sari Mason. They collected, I think, 259 bottles from different parts of the world. And these are the flags, cannot be seen terribly well, from the various countries. And they tested through some kind of optical system, and they counted the number of microplastic particles, all right? Sari Mason received an international sort of fame, BBC in Britain, Deutsche Welle in Germany, perhaps in Greece, I wasn't there, but certainly in Canada, CNN, CNBC, name it, because we have a very large number of plastic particles, microplastics, sized, micron-sized, all right? And, well, we drink them. Now, there have been other publications also, other research works. This particular work was carried out in Germany. And what surprised me in reading these works was the fact that we have too much polypropylene in microplastics. Now, perhaps this cannot be read, but according to Sari Mason's work, 54% of microplastic particles over the size of 100 microns, all right, were polypropylene. Okay, and the rest of the materials right here. So PEST, this is PET, is the same abbreviation, only 6%, but she was talking about large particles. In the work by Szymanski, here they have 84% is polyester, that is PET, 7% is polypropylene, 5% is polyethylene. Now, I'm really surprised about that because polypropylene bottles from the caps, I mean, they may represent less than 10%, right? So how come we find, even in the work of Szymanski, that they include all sizes of particles? They have 7% polypropylene microplastics more than polyethylene. Big surprise for me, but 84 for polyester, that's okay. So my only guess at the moment is that because polypropylene is brittle at temperatures below freezing, so it does become brittle, and maybe they break off the caps. This is just a guess. I don't know. This is something to be looked at. Let's take a look at bottle production. Okay. A bottle really starts off by being injection molded in the form of a preform. And this is a typical preform. It looks like a chemical test tube. And what I want to point out to you right now is right at the bottom, you see this mark over there. This is the so-called cavity gate mark. That's from where in the mold, there is a mold, and the polymer enters from this gate. There's a gate there in the mold, and when it's produced, there's a gate mark, which you can feel it. I have a water bottle right here in front of me, and I can feel it. There is a gate mark is right here, all right? Now, you might say, well, this gate mark is outside, right? Well, this preform will end up being this particular bottle. But how is it done? First of all, preforms are produced in large numbers, simultaneously in a matter of seconds. 25 years ago, I examined a mold with 96. That was 25 years ago. More recently, it was 156. I'm sure they do more than 200. Now, these preforms, they are dropped in a more or less random way. Sort of the mold opens up, all right? And the preforms, they drop down, right? Into some kind of a conveyor belt, I would say, maybe more like a conveyor series of buckets. And then they move on to the next station, and they are sort of lined up. They go to the filling machine. They get filled with Coke, water, whatever. And then the caps on the top, right there, they're pushed down. And it is hard to push it down, you know, because the cap has a ring at the bottom, which you saw it. And now I have twisted off my bottle right here. And of course, there is a ring at the bottom, which is separated by the bridges, tiny bridges right there. And so there's a lot of mishandling, manhandling, whatever you want to call it, of the preforms going to the bottles, and there are a lot of opportunities for things to break off. And let's take a look at another picture. These pictures I took with my regular camera when I go to the Greek islands. Well, I used it to take a picture of this caps. And you see the surface, you know, is not smooth at all, right? Magnification is whatever it is, you know, but And another thing, this is the gate mark, which is outside, all right? In this particular bottle, the cap, the gate is inside. There's a gate mark over there. And there's a good chance for this one, with all this manhandling, hundreds or thousands of bubbles circulating around, they are likely something to break off. And of course, this surface that's not terribly smooth, things can really shed off from there as well. So let me take a look at the injection molding process. And I said I only show over there just a mold with two cavities, right? And the polymer, molten polymer, enters from here, goes into there. You can see the gate over there, right? And then it will fill the sides and so forth. It will make, this picture is more like a cup, but it could be very similar, of course, to a cap, actually, for a water bottle. And right here, we're going to have the gate mark that I mentioned, all right, which protrudes a little bit. Also, there's a possibility of flash, which occurs where the two parts of a mold join together. For example, it's not terribly well shown here, but it could have a little bit of flash coming out of here. You might not see it with naked eye, but there's a little bit of plastic out there remains, and of course, after that may end up in the water. And of course, the porosity that we have seen on the surface. Now, there are things to do. Can we reduce the porosity? Yes, by increasing the pressure. Like, it takes some pressure, perhaps 10, 20 megapascals to fill the mold. But then we pack it with enormous pressure, which can go to hundreds megapascal, that is over 1,000 atmospheres, right? But if we can go up to 2,000, I've seen up to 2,000, maximum I have seen, 2,000 atmospheres, right? But if we put too much pressure to make the surface nicer, we may end up with more flash, you see? So you got to worry about the two things. So there are plenty of opportunities for these things. Now, I presented this problem to you to show that on the one hand, there are problems in recycling and there are problems in generation of microplastics, all right? Now, I'm going to move on with my statistics. Plastics production was in 1945, 1 million tons per year. 2020, 400, according to some other statistics, maybe 450 million tons. And from them, less than 1 million are biodegradable. And about this word biodegradable, I'm going to define it. Are they really biodegradable? Like if I throw this bottle of water or a biodegradable bottle of water into the ocean, will this biodegrade or will remain there? Or is it biocompostable that I have to ship it to a composting plant? I'm going to define it in the next few minutes. Well, the production of plastics and steel, they had the same volume in the 1980s, perhaps 88 or whatever, but the plastics production is increasing, as you can see, faster. And where do they go? A lot of it to cars. 2014, the average car had 200 kilograms. 2020, the estimate now, 2020, of course, is a year of Corona. the estimation is for 350 kilograms for the average car. So a lot of it goes there. Composites in aerospace. Of course, the stealth bomber is 100% composites, and it's carbon fibers and plastics held together. And of course, between the 777, 787, there's a big difference in composites. And here is the corrugated pipe. And here I'm in front of it. One of them produced with a customer of mine, is producing machinery for the production of corrugated pipe. And you see this one is corrugated, and it's really destined for municipal sewage systems. But this plastic pipe is not going to cause pollution because this plastic pipe is going to remain in the ground for 100 years, unless Grace, Professor, can correct me, but I think this is the expectation or the specification for plastic pipe to remain for 100 years in the ground, all right? So it's not going to cause an immediate pollution problem, right? There are some other kind of plastics that they do cause a big problem. And in the case of turbine blades, the power produced is proportional to the square of the diameter. So we get bigger and bigger blades, bigger turbines. The biggest, apparently, at least in 2019, maybe 2020, there's even a bigger one. The blades are 107 meters long, larger than a football field. The material that holds together the glass fibers, the carbon fibers, and the wood sits together is epoxy, which is a thermoset, which I mentioned, it's not recyclable. And the only place to, cheapest way to dispose of them is to send them to a landfill. And there is a municipality in Wyoming. They are making money by inviting people to bring the blades, expected about 8,000 per year for the next 4 years in the United States, to be buried for a fee, of course. But this is going to remain. The projection is by 2040, blades will be fully recyclable. Now, the biggest problem in pollution with plastics is packaging. You see the statistics right here. This blue color really is for packaging. 36% of global production. So we are talking about most of it being single-use packaging. We're talking about 150, close to 200 million tons per year of packaging are produced. An awful lot of it is not recycled. Now, who is polluting the oceans? Now, there are two, this picture, I took it again from some other publication, and this line refers to mismanaged plastic waste. China is a champion in mismanagement of plastic waste. In terms of pollution of the oceans, you can see over there, it is the worst pollution of the oceans, and the rest of the countries which pollute the oceans are from Southeast Asia. United States, on the other hand, is not contributing very much to ocean pollution. Well, some cities, they're smart. I like this one. This contraption, the city of Quinane in Australia, I think population is around 50,000. They came up with this contraption, which contributes quite a bit to reduction of pollution of the oceans. I hope such inventions are applied elsewhere. Now, what happens to all the plastics that has been generated since 1950 or 1945? There were not very much plastics produced those days, but from then on, the growth has been very rapid. Roughly only 9%, latest figures I have seen, maybe 12% globally is recycled. About 12% is incinerated, and most of it ends up in landfills, which creates a big problem. And plastics, of course, by their own design, their own properties, they will remain there for hundreds of years. How can we solve this problem? Well, the 3 R's: reduce, reuse, recycle. They have been heard for many years. Well, they are good things, reduce, reuse, recycle. What about biodegradable? Also. Now, in terms of recycling methods, we can separate them into 3 categories. Mechanical, which means that we take the plastic object, let us say this particular bottle that I'm holding, it can be chopped up, it can be granulated, it can be then, after granulation, you can pelletize it to make it more easily processable, eventually make new plastic products. Well, I will not make plastic bottles with recycled post-consumer plastic bottle, but I can make fabrics out of it, polyester clothes. And yes, many of the polyester clothes that we use, they have a significant amount of recycled polyester. Chemical means that we will have a chemical breakdown. We go back to the monomer, repolymerize it, can make different other chemicals, or the end solution perhaps would be incineration for energy production. That would create a lot of problems, of course, of atmospheric pollution. But chemical recycling is the preferred way to go if we recycle mechanically plastics, because after too many circles of recycling, too many cycles, the properties get degraded. Perhaps not the mechanical properties so much. Could be color. One problem that we have is with odors. A big problem is that lots of recycled plastics, they have a bad odor, which is very, very difficult to get rid of. But recycling should really start earlier. Separation. Now, you can see them in every plastic part that we buy. If we can separate them at home, what we buy, that would help a lot the plastics recycling industry. And there is certainly a lot of value. These prices fluctuate with the price of oil, of course. These numbers were correct. I think I collected them last summer. It gives you the value of the virgin plastic, roughly, sort of rough numbers per ton. Good recycled pellets can almost reach the value. You can get premium prices of recycled pellets because some manufacturers are obliged to include a certain percentage of recycled material. So a couple of times it happens that recycled pellets are more expensive than the virgin one, okay? So another additional benefit of mechanical recycling is that for every recycled ton of plastic, roughly about 2 tons of CO2 are saved because we don't have to go through the cracking process to start from oil or gas, produce the virgin polymer, so they're saving right there. Can they be sustainable plastics? Yes. Polyethylene, which is the most used plastic around the world, maybe I think it's over 30% of plastics is polyethylene, is produced right now in Brazil in industrial scale. It's not an experiment. They use sugarcane, and yes, they produced polyethylene in industrial scale and sell it, which is renewable, all right, not biodegradable, just like the fossil-based polyethylene, all right? So we can go this way. There is also, for PET, it wasn't done. It was more difficult to produce from plants, but right now it's Toray is a Japanese company. I had dealings with them in the past. I do remember that way back they were supplying a 50% plant-based PET, 50% based on fossil fuels. Now they do it, and apparently they are starting commercial industrial size production. What are the benefits versus problems of plant-based polymers? Well, obvious benefit is they are renewable. And of course, plants absorb carbon dioxide, roughly 2 tons of CO2 per ton of polyethylene produced. The trouble is that we use large agricultural land areas, deforestation. We take away good land from food production, and farming is still a problem in many parts of the world. It requires fertilizers, herbicides, pesticides, and they, in turn, produce their own pollution problems, right? Biodegradable plastics. They are mostly starch-based. Well, they don't really have the properties. So the big polymer is polylactic acid, right? They can undergo microbial decomposition in industrial compost facilities. If I throw a PLA bottle in the ocean, right, it will remain there for hundreds of years. Well, maybe not hundreds of years, but certainly for decades, all right? My PET bottle that I'm holding right now and drink water will probably stay for hundreds of years. PLA will stay in the ocean for decades. So, but in a compost facility, if the temperature is 70 centigrade degrees and whatever, humidity, the polymer is compostable, biodegradable, you may call it. There are polymers like Ecoflex from BASF in Germany, which is fossil-based, but it is biodegradable. some 20 years ago, there were popular this oxo biodegradable, like it's regular PE or polypropylene or PET, and you add this additive, and after you throw your plastic bottle away, it disappears. Well, it doesn't disappear. It fragments into smaller particles. I think it creates worse problems. So this oxo biodegradable, I haven't heard very much recently, but it was a solution that was proposed some 20 years ago. Problems associated with biodegradable polymers. We need collection and composting infrastructure. All right, so you throw them away, they will not go away. Just throw it outside in a forest or in the ocean, it will remain there for decades, all right? The properties have improved. A friend of mine just recently involved and said, PLA, it's a terrible polymer, he said, doesn't have good properties. Well, it has acceptable properties, but it cannot compete with polyethylene or PET. But PLA, it's acceptable, let us say. Big problem is disturbance of the recycling stream. They are not compatible, they mess things up. If you put together PLA with the other stuff, you're going to be in real trouble in the recycling stream. And it's difficult to separate them. They require production of corn, sugarcane, fertilizers, stuff like that. Now, what is the big challenge in biodegradable plastics? We would like to find a plastic that is easily processable. That is, we can make 200 preforms, right, in a few seconds, right? They should retain the properties that we like and we love and we're used to, and eventually decompose under natural environmental conditions, right? Like we throw it in the forest, we throw it in the street, we throw it in the oceans, and eventually it will decompose, right? Now, there is one polymer which has been developed lately. It's PHA. It was a company called Metabolics. I think they went bankrupt. They spent about $350 million. Things did not go well. They sold the technology to, it was an American company, it was sold to Korea for $10 million. However, there's a new company now where maybe half a dozen companies working on PHA, which according to Chemical Engineering News, its time has come. Maybe because PHA is biodegradable under natural environmental conditions. Like, yes, it does decompose in ocean water, but I'll have to wait. Can I make the 200 bottles in a few seconds? Because I'm a polymer processing engineer. There is pollution from tires. 60% of the tire is synthetic. 25% of it is left on the road, right? And of course, you're in Pennsylvania. Well, there was a big fire there. We had another big fire not too far from my university. And the local fire department were very proud because they managed to put it out in a matter of weeks, whereas they spent, in Pennsylvania, they spent months to get rid of it. Student of mine, former student of mine, is on the way to becoming a millionaire because he developed a devulcanization technology he's got a line producing 500 kilograms per hour, not too far from where I live. And he's selling his technology to other companies. So there's a way to do this, to recycle rubber tires. What about fabrics? Everybody will say that cotton is the most friendly in the environment. All right? And polyester is bad. Well, I wear 2 cotton t-shirts right now. I love it. It's a great material. All right? However, cotton has a very bad impact on the environment because of water needed to grow it. I did not know about silk. Silk apparently is very bad. I did not know about it till I prepared a talk not too long ago about the same topic. Linen, on the other hand, requires less water, less fertilizers. It's great, but I cannot use linen for everything else. Every clothing that we have, and it's difficult to make. According to this report and many other reports, the average pair of jeans requires 10,850 liters of water. A cotton t-shirt requires 2,720 liters of water. So this is really waste, you know. Now, the cotton industry, of course, is smartening up. They have systems of water recycling and stuff like that, and they are managing to reduce it. And while I was searching for latest sort of developments, they were giving numbers that can be done in modern facilities with less water. Polyester, on the other hand, has much lower water footprint. And polyester can be recycled. We can make clothing. And this number of 14%, 2017, is from Europe, all right? But it is increasing. So we use polyester to make clothing. But the bad news is in red. 1 load of laundry of polyester clothes can discharge 700,000 microplastic fibers. All right? So really bad news. What's the yearly human, I would say, consumption of microplastics? According to this review it was just a review. They did not do their own work, but they collected all the papers published, reviewed over 100 papers on the subject, and they came up with these numbers. From faucet water you get from the faucet, you know, from city system, you get about 458,000 microplastics per year. And from bottled water, the average person gets 356, you know, over 3 million, 4 million microplastics from bottled water, microplastics, you know, enormous quantities. And you may wonder, what's the effect on human health? Now, we don't really know all those things, but let me indicate you, where do microplastics come from? This is a study, was completed in 2019, and they are talking about the percentages of microplastic releases in the oceans. Depends on the part of the world. India and Southeast Asia roughly 16% comes from laundry, only 1.1% from tires. North America, 2.6% from laundry, almost 12% from tires. In fact, in California, I have seen some numbers. One research work from California, they were saying that it's 40% of microplastics in the oceans, in the Pacific Ocean, comes from tires, all right? So something to think about, how can we reduce microplastics pollution in the oceans? Now, there are some contraptions. Laundry bowls, filters. Now, laundry bowls are not the most effective. According to a paper that I have read, about 30% of microplastics will be removed if you have one of those bowls in a laundry machine. There are better systems that can remove 60% with filters, but they're more expensive because you really have to refurbish the laundry machine. You have to install the filter and so forth. But there are ways of going about it. So, question of microplastics now that end up in the water that we drink and in our dinner table, because we eat fish, the fish eat the microplastics, then we eat the fish and so forth. So this work was done at the Arizona State University, and they made a presentation. As you can see, it's a virtual presentation. I think it was last August or so, in September or August. And they found evidence of plastic contamination in every tissue of the cadavers that they examined, human cadavers, all right? And the presenter made a statement, at this point, we do not know whether this is a nuisance or whether it represents a human health hazard. I mean, the jury is still out, but I cannot imagine that microplastics would do any good. In fact, it's what I said before, that it's not just the plastic that is the polymer, which is a macromolecular substance. And more or less, it is inert. But when we talk about plastics, we include a lot of additives, all right? And those additives, they contain a lot of toxins. I mean, there's been a lot of discussion about bisphenols in milk bottles for babies and so forth. But, well, now these bisphenols are also in the microplastics, and they end up in the drinking water. And so we may have some problems. So what are the solutions? Well, the 3 R's, of course. And I have added redesign in research. We have to redesign, like the laundry machine in my residence here. There is a lint trap, all right? It's a laundry machine, and it's, of course, a dryer. The dryer has a lint trap. The laundry machine itself, there's no trap for the microplastics. Maybe we should redesign. We may have to redesign car tires. We may have to redesign, perhaps have less private cars on the roads and have more public transportation. We have to do research about everything. And But whatever solutions they come up with, they must be environmentally friendly, and at the same time, they must be economically meaningful. They must be also feasible. With that, I would like to thank you for listening to my seminars. And I have a message, and this message about saving the animals is connected with the pandemic, because in the country of Denmark, of 5 million, a couple of months ago, they had to exterminate, well, they say culled 17 million mink, all right, because they were infected with a virus. So using plastics can save the lives not only of human beings, but a lot of animals, and long live fur. Thank you for your attention. And I'll stop sharing now. Okay, thank you.
Thank you very much.